So this question raised by one of our friend Mr. Gagan particularly caught my attention. It is a relevant question in the field of thermodynamics, but our point of view, from our course point of view, it's not to explain that detail. Explain it using this video. I will not be. I cannot. So I have decided to prepare this video. So the question, this question, to answer this question, you'll have to understand what is the difference between reversible and irreversible process. So what is mean by a reversible process? So I think we'll start from that point. So reversible process. So in order to understand the reversible process, we need to understand another important concept, which is called quasi-static process. I have heard about quasi-static process in your class. So in fact, in thermodynamics, we have to start from when we start from the basics. We have to study all these things. In mechanical engineering, there is a course thermodynamics in the third semester, where we are the entire course is thermodynamics. But whereas in your case, you have thermodynamics for a single a part of your first module. So we cannot go to that detail. So again, still, since this question is raised, I'll try to answer this. So what is meant by a quasi-static process? So suppose we'll start from the most common example we encounter in this course, that is a piston cylinder system. So we have a cylinder, then there is a piston. So this is our piston. So inside the cylinder we have an ideal gas. So assume this gas is now in equilibrium position. So if it has to be in equilibrium position, there is one more thing is required, otherwise it will not be in equilibrium, because this gas will be applying a continuous it will be in continuous motion, and it will bombard with the walls of the container as well as the piston. So if we have a vacuum here, the force exerted by the gas on this piston can lift off this piston, or the piston can simplify off, because this piston is weightless, as well as at this point this is also frictionless. So this piston can slide without any friction, and it is also weightless. So if there is nothing preventing it from flying off, this system will not be in equilibrium. So I am adding another weight here. So we have a weight here. So this weight will keep the system in equilibrium, because this weight will apply a force in the downward direction. So when that becomes equal to the force applied by the pressure of the gas, then the system will be in equilibrium. Okay. Now this is just like a compressed spring. If we have a spring, you cannot keep the spring in a compressed position. You will have to put a load over it, so weight over it. So we can keep that spring in compressed position. The same thing happens here. So the force, restoring force exerted by the spring will be equal to the weight applied over it. So the same situation here. So this system is in equilibrium. So we can say that its pressure is, say, P1, and temperature is T1, and volume is also fixed. We have volume V1. Now quickly I am going to, so this is the state 1. Now quickly I am going to the state 2. What happens when, so I am going to copy the same figure here. So piston weight and the gas particles. So now I am going to do some magic. By somehow I vanished half of this weight. Let us say I am going to erase it, half of this weight. So now we have only, earlier we have say 1 kilogram, now we have only 0.5 kilogram weight. So suddenly what happens, that will throw the system out of equilibrium, because here the force exerted, the pressure exerted by the gas molecules was in balance with the weight. So now the weight is suddenly reduced to half. So this force, the pressure force will try to lift the piston out of the cylinder. So that way what happens is, so these particles will feel a low pressure because there is no force resisting it from the top. So what happens, the system will be out of equilibrium, so this piston will move up. Then since it happened very suddenly, the piston will start vibrating a bit, so we'll have some oscillations, just like the same thing happens when we remove this weight from the spring. The spring will be moving or oscillating back and forth for some time, then it will settle at some length. So that's what happens for a spring. Same happens for this gas, this cylinder. So it will suppose that piston has moved to this point, so we have half weight over it. So now we can see that volume has almost doubled, because the pressure is that weight is halved. So now only half of that total force is acting here. So the pressure that gas expands, then pressure decreases and volume decreases. Now assume that we have waited for a long time, so that the system is now in equilibrium. So at this point we have our equilibrium values. Say pressure is P2 and temperature has changed, because pressure decreases and temperature also will decrease by Boyle's law, we know that. Then volume also we have sorry, not Boyle's law, anyway, by ideal gas equation we know that when pressure decreases, temperature also will decrease. Then volume has increased, because it is expanded, so volume has increased. So this is our state 2. So when we represent these two states in a PV diagram, we can see that we have a pressure on the y-axis and volume on the x-axis. So at state 1 we will represent, so let this be P1 and this point be V1. So this is our state 1. Then state 2, again this is also in equilibrium, so we can represent the state 2 also. Pressure is P2 and volume is V2, so this is state 2. So now the question is, what happens in between? So we have state 1 which is in equilibrium and state 2 which is also in equilibrium. But in between, our system was in a very random state. It was not in an equilibrium state. So how can we know, is there any way to know the path of this process? Which path is followed by the system during this transformation? whether it was a constant volume process, whether it was a constant pressure process, or is it isothermal, isobar, adiabatic, what type of process happened here. Is there any way to know that? Think about it. In fact, there is no way of knowing it. You only have state 1 and state 2. We don't have any intermediate points between state 1 and state 2. Because this type of process happens in split of a second. So the system is in equilibrium, not in equilibrium. For example, if you consider why the system is not in equilibrium, because in this case we have also we have seen that volume will be oscillating. So at a particular time point, the volume will not have a fixed value. Volume will fluctuate. Pressure also, when we suddenly remove the half of the weight here, when we suddenly remove the half of the weight, this gas particles at this region will suddenly came to know about that. So it will come, suddenly it will come to know about that. So the gas particles at this region will suddenly come to know about that situation. So the pressure will suddenly reduce at this region. But when we consider this region, the particles at this region may not even know about that weight has been removed, because it will take some time for that pressure wave to reach at this position. So here it will be pressure will be high, and here pressure will be low. So in the same system, at different points you will have different pressure values, and since the pressure is different, temperature also might be different. So temperature value also might be different. So the same system, so we cannot represent a system if we have such a situation that we can represent a state only if that state is in equilibrium. Otherwise this type of issues come. One part of the system there will be one pressure, other part will be other pressure. So we cannot, the entire system we cannot represent as a single pressure or single temperature. So we cannot represent, we cannot define any path for this process. So we'll keep that aside and we'll consider another process. The same idea will extend to. So we will consider the same system. Assume this is the same system. We have a piston cylinder, and inside we will have gas. So instead of having this single weight, here I am having let us say the same weight, but it is like a heap of grains of sand. We have some sand here that amounts to same weight we have shown here, but instead of having a single block, we have grains of sand here. So how can we now, what is the difference? What is the difference between these two? So in this case, if you have grains of sand, we don't have to vanish half of the weight suddenly. So that created this unbalance and problems. So instead of that, we will do another method, that we will take the system, instead of removing the weight in one go, what we are going to do is we will remove the weight as one grain by grain. Each grain of sand we will remove. If we remove one grain of sand, say, then that causes a small disturbance in the system. So pressure will slightly reduce, but we will wait for the pressure to reach equilibrium everywhere inside the system. So that that change may also have caused some temperature change, but still if we wait enough time, the temperature will be balanced, or that heat transfer will happen from one part of the system to other, and the temperature also will reach the equilibrium. So after taking one grain of sand, if we measure the pressure and temperature, we can show that because that system is still in equilibrium, so we can mark that pressure and temperature. Say pressure has slightly reduced and pressure and volume. Pressure has slightly reduced, volume has slightly increased. So after removing one grain of sand, similarly we can take another grain, and grain by grain we can remove sand from the system, and we can reach the same state, that is we can remove half of the weight of the sand from the system, from the piston. In that case, at each point the system is almost in an equilibrium position. So we can represent the path as a series of the succession of these points, and finally we can join them, and we can see that now that path is almost, we can define the path in which that problem, this process has happened. Whereas in this case we cannot define that. We have no way of knowing which path the system has followed, but in this case we can understand the path followed by the system. So this type of process, this is actually an imaginary process. We are not actually in the real world we are not doing this experiment, but we are imagining such a process. So this type of process is called a quasi-static process. It is called a quasi-static, means quasi means quasi, the word meaning is it's almost. The system is always almost in equilibrium. In each step, if we consider, the system is almost in equilibrium. It's not entirely in equilibrium because we are changing things. When something is changing, it will not be in equilibrium. But almost it is in equilibrium because we are doing the process at a very small rate, step by step. So that type of process are called a quasi-static process. So why did I talk about quasi-static process? I was starting with the reversible process. So what is meant by a reversible process? So reversible process has should be, for a process to be reversible, there are mainly three conditions. So one is it should be quasi-static. That means it should be equilibrium at all the points. So if we can only represent if we want to represent a process in a PV diagram or PT diagram or any thermodynamic diagram, it should be quasi-static, otherwise we cannot represent. For example, if this type of process, we cannot represent that in a PV diagram. So it's only if the process is quasi-static, we can represent that on a PV diagram or PT diagram, any thermodynamic diagram. Then, so that is one condition. So it should be quasi-static. Second condition is, yes, also assume that there is no friction between piston as well as the cylinder. So for the equilibrium, for a process to be reversible, should be quasi-static and there should not be any friction. Nowhere in the system, this is a simple system we have considered, but whatever be the system we are going to consider, everywhere inside the system we should not have any friction. If there is a friction, then that process is not reversible. So if it is not quasi-static, then also the process is not reversible. Then the third is no heat transfer, it's not heat transfer across finite temperature difference. So I will come to that. So first, what is mean by reversible process? A reversible process is something that can be reversed without changing anything in the system or surrounding, or without altering anything in the universe. So for example, if you are taking a grain of sand and there is no friction in the piston, so if you are keeping that grain of sand back to the system, back to this heap, the system will simply go back to the earlier initial state without any change in the system or surrounding. If that is possible, then that type of process is reversible process. What happens when there is a friction? If there is friction, when we take the grain of sand, so there will be a rubbing between the piston and the cylinder. So that rubbing, that friction will produce some heat. A small quantity of heat will be produced. So that will come to the surrounding, or it can increase the temperature of the system, whatever. So when we replace that sand particle back on this piston, this heat cannot be, it will not, the friction is only we cannot have friction the reverse that friction, that it will not take the heat back when we put the sand back to the system. So whatever work we are doing against the friction will always, it will be converted to heat. We cannot recover it. So if there is a friction, then system is not reversible. And the third condition, suppose we have a heat transfer between two objects. So we have one object here and other object here, which are in contact with respect to each other. When so this is at high temperature, this is at low temperature. So we know that heat flow will happen from high temperature to low temperature. When a heat transfer has occurred, we cannot reverse this process. In this case, we cannot, if there is a finite temperature difference between the two parts of the system or two systems, we cannot reverse the heat transfer in this case. So if there is a finite temperature difference, then that process will become irreversible. Instead, if you have two components which is almost in the same temperature, they have only both the systems are almost in the same temperature. So if we slightly increase the temperature of one system, there will be heat transfer from this body to that body. So that can be reversed if we slightly decrease the temperature. If we infinitesimally decrease the temperature of this system, this heat transfer also can be reduced. So if there is a very infinitesimal temperature difference, that heat transfer is a reversible type. But if there is finite temperature difference, that is, let us say we have 10 degree and 5 degree, then there is a 5 degree difference. So that type of heat transfer is not reversible. So if there is such a type of heat transfer in the system, then that process also will be irreversible. So these three conditions, if these three conditions are satisfied, then only we can have a reversible process. Now you might have understood the reversible process. So it will not happen in the real world. It is not it is only an imaginary process. We can't have a reversible process in the real world, because the one thing is, it is most of the process will not be quasi-static. It will happen instantaneously. So, but that we can slightly we can adjust by doing it in a very small steps. We can make it almost quasi-static. So this is almost possible, but friction, no friction, that condition we cannot achieve. Similarly, if there is no temperature difference, heat transfer rate will be very less. So all practical systems, we cannot have that much small heat transfer. With that much small heat transfer, we cannot run practical systems. So this is mainly these two ideas are not practical at all. So we cannot have reversible systems in real life. Then I'll come back to this question: is there both reversible and irreversible process for isothermal expansion? So the answer is yes, because if there is theoretically, answer is theoretically yes, but practically we can't have a reversible process in practice. Okay, so why it is yes? So if there is, if we assume these conditions, if it is quasi-static and no friction and no heat transfer across finite temperature difference, then that process is reversible. If there is friction in a process, if it is quasi-static, we can represent that process in a PV diagram. So it will look like a isothermal process, but there was some friction between the piston and the cylinder, then that process is not reversible. It is a irreversible process. Similarly, for if there is a heat transfer with finite temperature difference, in that case also system will be reversible. But in our last class, I have mentioned specifically a reversible process for in isothermal process as well as adiabatic, isobaric and isochoric process. I have not specifically mentioned this reversible that term because that assumption we have not invoked in derivation of those work and heat input in those systems. We have not invoked that assumption. We can in isothermal process, we have seen that we have assumed that PV is equal to constant. So, we know that PV is equal to MRT. So temperature constant means PV equal to constant. So that doesn't have anything with reversibility or irreversibility. If it is reversible or irreversible, that is true. So that is the only assumption we had in that derivation for calculating the work done. Similarly, for other processes, isobaric or isochoric process, we have condition that either V equal to constant or P equal to constant. In that case also, we don't need any assumptions regarding reversible or irreversibility. But in case of a adiabatic process, we assume that PV raised to gamma equal to a constant. So this assumption comes from reversible condition. So this is true only for reversible adiabatic process. That's why I have mentioned specifically reversible adiabatic process. Otherwise, all process we have mentioned we are going to study, or we have studied in our class, are ideal processes, and they are all reversible process because we are not considering any friction or temperature heat transfer with finite temperature difference. So all this in this entire course we will be talking about reversible process only, even though all practical processes are irreversible. So thank you for this question. Because of that, actually I decided to skip this portion because it's not we don't have any time for that in our syllabus. But again, since you asked this question, I had to do it. So thank you very much.